This instruction is two examples of complex motion for forces and moments. In this example, we have a truck that has a known acceleration of 6 meters per second squared, so it's accelerating like this, starting from rest. We want to find the initial angular acceleration alpha. We're given the mass of the ladder, and the fact that it's a slender rod, so we'll treat it as a slender rod for the moment of inertia. The way this works, the steps that you use, is that you'll first sketch the free body diagram. Sketch the free body diagram. Find the point for which you know the acceleration, as example A, for an example. Draw the acceleration diagram and write the relative acceleration equation. A is equal to A plus A. A is equal to A plus A. What you want to do, and those are all vectors, what you want to do is write unknown is equal to known plus relative. So in our case, the unknown is going to be G. The known is going to be A. And the relative is G relative to A. And draw the acceleration vector. Then the normal would point from G toward A, and the tangent would point counterclockwise from around the path of G rotating around A. Standing on A, watching G rotate counterclockwise. There's the relative acceleration equation, all vectors. And then you can substitute for the acceleration of A, for G relative to A, you can substitute the normal and tangent values for those omega squared r and alpha r. Then you need to write two force equations, two of these, where this Q represents the axis for which you're writing those. For example, you may want to write the forces in the x, so you'd write some of the forces, go get all of the forces in the x direction, and set them equal to mass times the acceleration of G, which you would get from right here by combining these in the x direction. And write two of those, x and y for instance, or x prime and y prime, normal tangent, and so on. And then you need to sum the moments. You can choose whether you want to sum the moments about G and get I about G alpha, or sum the moments about A, where you have to have a correction factor. This correction factor, it works just like a moment, clockwise and counterclockwise, where this represents the force. So you take these acceleration vectors that you drew right here, and treat them as moments about point A, either clockwise or counterclockwise, where the distance is the perpendicular distance from T to A or from G to A. So that's those are the steps. So let's go do these steps for this problem. So the first thing we do is draw the free body diagram. Now notice that we're going to assume this ladder just lifts off. With this acceleration, we're going to assume it just lifts off at B. In other words, at point B, the ladder is not being held up or down. It's not positive or negative. It is simply zero. So there's the free body diagram. Those are all the forces. Write the relative acceleration equation. G is A plus G relative to A. Draw the normal tangent coordinate system. Here's A, here's G. Here's the normal pointing from G toward A. And notice that it's from rest, so this is 0. Tangent is counterclockwise, alpha r. And then using that, we can write, we can simply go get the x and y components of G relative to A. Notice these numbers right here. This acceleration is for G relative to A. We can go write the components. Notice that this vector is in the third quadrant, so it's going to have a negative x and a negative y, and its quantity is going to be alpha r, alpha times r. Now this has to be the perpendicular distance from here to here. So in the x direction. So it's going to have to be the x component, that, times the perpendicular distance, which would be this. And then the y component, which would be this, and then the perpendicular distance, which would be this. So that's what these two are. They're the perpendicular distances. So you can calculate those numbers, and then we can use that to write an expression for the acceleration of g, because what we just wrote was the acceleration of g relative to a. And we can do that in the x direction, and it becomes, you look back at your acceleration diagram, grab everything in the x direction, it becomes minus 6 minus alpha r. So minus 6 minus alpha r, which we get from right up here. And then in the y, it's 0. There's nothing going on in the y direction for a. The acceleration of point A has no acceleration in the y direction. And then off of alpha r, you get minus alpha. Once you get those accelerations in the x and y written, then you can sum the forces off of your free body diagram, and set it equal to m times the acceleration in the x direction. Two unknowns, so you can't solve it. So then you need to have more equations in order to solve. You can sum the moments about point G on your free body diagram, and they are AX and AY. Both have components, so it's AX times this distance and AY times this distance, and those are those distances there that we found before, is equal to I about G alpha, and this comes off of your diagram for those moments of inertia, and there's alpha. So you still have, now you've introduced one more unknown, so you need another equation. So you sum the forces in the y direction from your free body diagram. Go get all the forces in the y direction. They are minus 20 times g plus ay. So that's what goes right over here. Those are all the forces in the y direction, is equal to m times a in the y, which you get right up here. And then you have some algebra to do. That would get you a 90% on a test or quiz if you had that all set up and you were ready for the algebra, and then you would solve and get alpha. Let's do one more problem. Let's go through one more problem. Notice this is a rolling. This is a spool rolling. You follow the same steps. You first draw the free body diagram, find the point on the axis, on the object that you know the acceleration. We have a spool. We're given the moment of inertia, the radius of gyration, so we can find the moment of inertia. We know the coefficient of kinetic friction. So notice how this spool works. It's actually tied off right here. So that is the point for which we know the acceleration. The way rolling works is wherever it is constrained, it acts like a pure rotation. So the way this works is that if this is tied off here, it actually has to slide along this surface in order to accomplish rolling, but being constrained by the cord being tied off. So we're going to work in an x prime, y prime direction for our free body diagram. It's going to be tied off with a tension in that cable, mg, normal force coming off the surface, and since it's sliding, you're going to have a mu times n sliding on that surface. Here's our acceleration diagram and the normal tangent coordinate system. This is normal tangent. This is from rest. So omega squared r is going to be 0. In the normal direction, omega squared r is 0. And here's alpha r. Here's our acceleration of g is equal to acceleration of a. I guess, oh, that's b, I guess. b plus the acceleration of g relative to b. Those are all vectors, so if you're working in the x, x prime, and so on, you need to be careful with those. So there's the normal tangent coordinate system. You can sum the forces in the y prime direction on your free body diagram, and you get n, in the y prime direction, minus mg cosine theta. We're working in the y prime direction now, in this direction. And you know those numbers, so you can find n. And in the y prime, that's equal to 0. There's no acceleration in the y prime direction. That's why you'd like to work in the y prime direction. You can sum the forces in the x prime direction. They are plus t minus mu times n minus mg sine 30. And that's equal to m times a in the x prime direction. And you get that off of your acceleration diagram. And notice it's in the negative x prime direction, so it's minus m times 0.3 alpha. Now let's go back and see where that 0.3 came from. Notice it's from there to there. It's from G to the point of rotation. And that point of rotation is point B. And then you sum the moments about G and get I about G alpha. So off of your free body diagram, you sum the moments about G. Here's G. N doesn't cause any moment. Mg doesn't cause any moment. So you simply have T and mu times N. T is times 0.3, and mu times N is times 0.6. So, and clockwise and counterclockwise. And this is the moment of inertia is the mass times the radius of gyration squared times alpha, and then you solve.